Alright, welcome to the 6th week of our machine learning course. This week we will be working on decision trees. As usual, we will start with summary of the last week, and then we will see definitions of decision trees. Then we will see how we can train decision trees and how we can use them for regression problems. Then we will do some examples for missing values and categorical values in our dataset, and then we will see how we can do end-to-end modeling. Concerning the summary of the previous week, we had seen the concept of linear separability, and we have seen these two sets are linearly separable because there exists at least one line that can separate this class from this class, and these sets are not linearly separable because we have no single line that can split these two sets from each other. Then we have seen the concept of support vector machines, and we have seen we can use support vector machines to classify linearly separable problems as well as linearly non-separable problems such as this one. And then we have seen how we can use binary classifiers such as support vector machines or logistic regression for multi-class problems, as in this case we have more than two classes. It's not just ones and zeros, we have more than one classes, and we can use a single binary classifier with two strategies. We can either use one-to-one or we can use one-to-rest strategies in order to train a binary classifier to solve a multi-class problem. So coming back to the linear separability, since we have two classes in this case, we have a lot of lines that can split those two classes into two, such as this one and this one. But as in this case, we have no single line that can split pluses and minuses. Therefore, this set is linearly non-separable. Okay. And more complex examples, we have more data in these data sets, and there are a lot of lines that can split the red triangles from blue circles, as well as this one. We have at least one line that can split this class from the blue circles. And in this case, since we have a red triangle here inside the circles, even if we have a line that can split most of the triangles from the circles, since we have this triangle here, this data is linearly not separable. And this data obviously not separable because there is no single line that can split this in a good way. And we had seen an iterative algorithm that can find a fine line that can split linearly separable data into two, and we had done a Python example on that. Now we saw the support vector machine concept. We made the mathematical derivation, and in the end we came up with this equation, and that we have seen here that the whole minimization process depends on the dot product of samples, and depending on the dimension we take the dot products, we are able to solve problems that are not linearly separable. Okay. In this example, we see a support vector machine median line and the gutters of the support vector machine, and the whole idea behind the support vector machines is to try to maximize the distance between two gutters. And if that's a linear problem, then our median is a line and the gutters are lines as well, and the gutters pass through the points that are on the boundary, since the aim of the algorithm is to maximize this distance between two gutters. And what we have seen with support vector machines is it doesn't only solve linearly separable problems, but it can solve linearly non-separable problems as well, such as this one. In 2 dimensions, it's not possible to find a single line that passes through this dataset and splits into two. But if we increase the dimension of this data, such as this one, we can put a hyperplane over here, and then we can split this data into yellow and red circles. And that's the whole idea behind support vector machines. We carry our data into a higher dimension by using the dot product in higher dimensions, and then we create our median line or median and the gutters in that higher dimension. Then we can actually solve problems that are linearly non-separable. So if you remember the equation, the whole idea was to use the dot product of samples in higher dimensions. And that trick is called the kernel trick. Not getting the dot product in second dimension, but we can use other dimensions. And depending on the function we use for dot product, we can use radial based functions, polynomial kernels as homogeneous as in this equation. A polynomial kernel is homogeneous as in this equation. And using a higher dimension for the dot product is called the kernel trick. And that's basically the mathematics behind support vector machines, and that's basically the idea behind the support vector machines. Just get the dot product of samples in a higher dimension. And then we have seen the multi-class classification problem. We saw that there are two strategies. We can either use a binary classifier such as support vector machine or logistic regression, or we can use a natively multi-class classifier. If we want to use a binary transformation, we have two strategies. We get one-to-one. We calculate the classification one-to-one for each class, or if we have a one versus rest, we calculate the classification for each class versus the rest. And we have some native classifiers such as decision trees that we will be seeing this week. If we just use this native multi-class classifiers, we don't need to do any trick like this. We can just use this classifier and we can solve a multi-class classification problem. And revisiting the quiz of the last week, SVM stands for support vector machine. SVM tries to maximize the boundary gap between classes. That's true. That's the whole idea behind support vector machines. SVM can handle only linearly separable classification problems. That's false. That's why we have support vector machines, to solve linearly unseparable problems. RBF stands for radial base function. Getting the dot product of samples at a higher dimension is referred as the kernel trick. That's an important question. F1 score favors high precision and high recall. Remember, F1 score is the harmonic mean of precision and recall. So if you want to have high F1 score, you need high precision as well as high recall. Which of the following are kernels that are used for SVM? Basically all of them are kernels for the support vector machines. A linearly inseparable classification problem can be solved by using a higher dimension of the feature vector. Yes, that's true. That's the whole idea behind support vector machines. A sklearn function to create an SVM model is SVC. SVM works super fast for large number of features. That's false. As we have seen in the example of the last week, once we were training the support vector machines with the MNIST database, that was quite slow actually. And if we have too many features, support vector machines lack speed. Okay, so that was basically the summary of the last week. Now let's start with the introduction to decision trees. Let's see what a decision tree is. But before doing that, you need to install GraphViz on your virtual environment. If you don't remember how to install a library on your virtual environment, please revisit week 2. There you have basically an explanation on how to install Anaconda and how to install libraries on Anaconda. We will be using GraphViz in order to visualize our decision trees. Okay, so what a decision tree is. A decision tree asks a question and classifies the input based on that question, such as this one. Is person taller than 180 centimeters? If the answer is yes, then this person is classified as tall. If the answer is no, then that person is classified as not tall. This is a very simple tree, but this is a decision tree basically. This is the question we ask, and usually we use the left side of the tree as the positive answer and right side of the tree as the negative answer. So why do we need decision trees actually? Classifying fruit based on its description does not benefit from a calculation of Euclidean distance or L1 distance at any point in the process. So we need an alternative method that can attack these specific problems. Assume that we have categorical data, right? And if you have categorical data, Euclidean distance or L1 distance, those are mathematical distances, doesn't mean anything. Let's say you would like to solve the problem of classifying apples and oranges based on their color. And the color is a categorical value. For example, oranges are yellow and apples are red. And these are not numerical values. So neither Euclidean distance nor L1 distance doesn't mean anything. Okay. For these kind of problems where we have categorical data, we need classifiers like decision trees. And you can have basically more than two levels, such as in this case. For example, this tree asks whether the person is hungry. If the person is hungry, then the decision is you need to eat. If the person is not hungry, then we ask again whether the person is hungry. If the decision is positive, because it's on the left side, then the decision is maybe it's time for a snack. And if the answer is no, that's on the right side of the tree, then no need to eat. So these are our decision leaves. So this is a more complicated tree. That's an example. In this tree we have both numerical data as well as categorical data. What we mean with numerical data, for example, the age of the person, right? So the question we ask in this node is whether the person is 40 years old or older. Since we are using a numerical value as the age, that's a numerical data. And if the answer is yes, we follow this branch. And we check the resting heart piece rate. If it is bigger than a number, we go in this direction, we go to the left. Then we check whether that person eats donuts. So this resting heart rate is another numerical data, and eats donuts is a categorical data because there's no numerical thing here. Okay. And that's same for the right side of the tree. We ask the question whether the person is older than 40 years old or older. If the answer is no, then we check whether the person eats donuts. If the answer is yes, you don't need to worry, the decision is. If the person is older than 40 years old and the person eats donuts is not true, the person doesn't eat donuts, but the resting heart rate is higher than a number, then we suggest an exercise. If the answer to this question is no, then everything is okay. So we basically ask questions with the decision tree in order to split the data into parts, and within that parts we ask more questions until we come to a decision. And why do we call this data structure a tree? Let's make some definitions. All these things, all these blobs that are covered with circles, they are called nodes. Okay. And this specific node over here, that's called a root node because it's on the top of the tree. And all these guys, these lines are called branches. And these specific nodes that doesn't have any branches are called leaves. Okay. And these leaves are actually the decisions. If you follow this, for example, that's a fruit classification. We are asking the color. If the color is green, we follow this branch. We ask the size. If the size is big, for example, we classify this fruit as watermelon. If the size is medium, we classify it as apple. And if the size is small, we classify this as grape. So we have levels as well. This root node stays on the level 0. And these branches over here, they stay at level 1. These branches over here, they stay at level 2, and these branches stay at level 3. And by this data structure is called a tree. You can just check this image. That's an upside down tree. This is the root of the tree, right? And this is the root of our data structure. This is the trunk of the tree, and these are the branches of the tree, right? And these are the branches of our tree. And these are the leaves of this physical tree, the upside down physical tree. And these red blobs, red nodes are called the leaves of the tree as well. So that's why we call this data structure a tree. And since we make decisions by using this tree, this is called a decision tree. And how do we use decision trees? That's basically the question we need to answer. The whole idea is we would like to convert our table, the data table, into a decision tree. And as you see, we have 3 independent variables here, and we have a target variable as heart disease. We have chest pain, good blood circulation, we have blocked arteries. What we want to do is we would like to convert this table into a decision tree. And we need to find which one will be at the root node and which one will be following the root node on the left side and on the right side. So we just need an algorithm to construct the tree by using the data. And the data contains the independent variables as well as our target variable. And the first step is to find out which of the following independent variable will be the root node. Okay. In order to do that, we need to analyze our data. For each independent variable, we create this small tree or subtree, let's say. And then the root of this subtree is the independent variable itself. Then we have on the left side the first category, which is heart disease, yes or no. And in the right side, we have again the target variable classes with heart disease, yes and no. And in order to read this subtree, the person that have chest pain, yes, on the left side. So this number over here, 105, means the person has chest pain as well as heart disease. Okay. And the person has chest pain, but he doesn't have heart disease. These are the number of people in that situation. So looking at this row, for example, the person doesn't have chest pain and doesn't have heart disease. That person, that row, falls into this category because the person doesn't have chest pain and the person doesn't have heart disease. Okay. So we create the same table for all independent variables. We have good blood circulation as well as blocked arteries. We do the same for all independent variables. Then we somehow need to make a decision which of these subtrees will be the root of our decision tree. And once we check basically the subtrees, what we see is none of the leaf nodes are 100% heart disease or not, right? Just look at this. We don't have any leaf node, decision node that says 100% heart disease or not. And this concept is called impurity. The data is impure. And we will be using this impurity concept in order to construct our decision tree. And we will use a metric called Gini index, Gini impurity measurement, that's to say, in order to create our decision trees. And since this is a level of impurity that's measuring the impurity, if you have identical objects, then the impurity is low because they are pure. Impurity is the opposite of purity. So if you have something like this, then your impurity is low. If you start to have things that are not identical, then you have a medium impurity. And if you have stuff that are not really identical, then you have impurity high. Okay. For example, this set have lower impurity than this one because this set is more diverse. And the Gini index is a mathematical metric that's measuring the impurity in your data. So how do we measure the Gini impurity? We basically draw some examples from the dataset, such as this one. We have 10 data here. We basically draw 2 randomly and then check whether they're from the same class or not. And as you see, if the impurity is low, then the difference draws out of all the draws is low. For example, in this example, this is different, this is different, this is different, and this is different. So 4 out of 10 draws are different. But in this case, since we have more than 2 classes, the impurity is high. And once we draw things randomly, we come up with more different couples, such as this one, this one, this one, this one, and this one. So we have 7 out of 10 different draws. And Gini index is basically probability of picking 2 distinct elements. Okay. And how do we mathematically calculate this? Basically, we have this table with all the data as the rows and columns, and we basically measure these areas. Okay, these are the non-distinct elements, and 1 minus the area of these non-distinct elements gives us the Gini impurity index. So we have 10 elements here, we have 10 elements here, so the whole area of this matrix is 10 by 10. Okay, and the area of the identical squares is 4 by 4, 4 times 4. The area of identical circles is 3 by 3. The area of identical triangles is 2 by 2. And the area of identical star is 1. And in order to calculate the Gini impurity, what we basically do is 1 minus, that's everything, minus the area of identical classes. And in this case, that's the area of blue, area of red, area of green, and area of yellow. And once you get this, you calculate the Gini index. And basically, mathematically speaking, that was a 4 by 4 square, that was a 3 by 3 square, that was a 2 by 2 square, and that was a 1 by 1 square. Basically, these are the areas of the identical classes. 1 minus the area of identical classes gives us the Gini index. And that's a very high Gini index in this case, 0.7. Then how do we calculate the Gini impurity index for our subtrees then? The thing is, we calculate 3 Gini indexes. 1 for this leaf, 1 for this leaf, and 1 for the root node of the subtree. And the way we calculate the Gini index for this leaf is 1 minus probability of yes square minus probability of no square. And in this case, it's 1 minus 105, which is this number, divided into the total number of patients. Okay, minus number of no's, that's 39, divided into the number of all patients square. And this is 0.395. This is the Gini index for this leaf. Okay, and we do the same calculation for the right leaf as well, and we come up with a Gini index of 0.3396. And from these 2 leaves, we need to calculate another Gini index for the root. And the way we do it actually is, we have 144 people on the left side and we have 159 people on the right side. And the total Gini impurity for chest pain is 144 divided into the total number of patients times the Gini index of the left side plus 159 divided into the total number of patients times the Gini index of the right side. So this is 0.364. Okay. And once we calculate the Gini index for all these subtrees, chest pain, good blood circulation, and blocked arteries, we select the one with lowest impurity as root node. And in this case, it's the good blood circulation, right? So we select this as the root node for our decision tree. Now that we selected the good blood circulation as the root, we have a tree something like this. So this is the root node. And now we need to select the left side and the right side of our tree in order to construct our tree. So let's see how we calculated the Gini index for good blood circulation. That's basically the Gini index for this leaf node, and this is the Gini index for this leaf node. And we know how to use these two Gini indexes in order to calculate the Gini index for good blood circulation. Okay, now we have this number as the Gini index for this node and this number for the Gini index of this node. Okay, and since this has lower impurity, we will continue from this node, and we will check chest pain and blocked arteries for the Gini indexes, so that we will decide whether we will be splitting this node, whether we will be using chest pain or we will be using the blocked arteries. In order to do that, we will now reconstruct these subtrees again. With the knowledge, we will be using people with good blood circulation. Okay, since this is the left side of the tree, we will be using just people with good blood circulation. And for the right side of the tree, we will be using people only with bad blood circulation. Okay, therefore the subtrees changed for chest pain and blocked arteries. Now that we have this subtree for chest pain, we will be calculating the Gini index for this node, and we will calculate a total Gini index, and we will be coming up with 0.3. Now for blocked arteries, for people with good blood circulation, the blocked arteries subtable will have the Gini index of 0.29. Okay, and when we look at these three numbers, 0.349, 0.29, 0.3, 0.29 is the lowest impurity. Therefore, we will be using blocked arteries on the left side of our tree. Okay, and the tree will look like something like this. Now we have the root node as good blood circulation. We have the left node as blocked arteries. And then we will apply the same procedure in order to construct our tree. For example, for this node, we will be selecting the chest pain, but for this subtree, we will have people with good blood circulation and blocked arteries. And out of that people with good blood circulation and blocked arteries, we will select people with chest pain, and then we will reconstruct this subtree, and we will insert the subtree into the left side of our blocked arteries tree sub-branch. And that's what it looks like when we actually apply chest pain here. And then we will take a look at the right side of the blocked arteries. Here we have this subtree, okay, and we have chest pain. For the chest pain with good blood circulation and non-blocked arteries, we have a Gini index of 0.29. Okay, but for this node, we have 0.2 as the Gini index, which basically means this node has a lower impurity than this subtree. So we don't need to split this. So we leave this node as a decision leaf. Okay. And our tree then looks like something like this. Good blood circulation, blocked arteries, and chest pain. So we construct the left side of our tree. We apply the same procedure on the right side of the tree. And once we construct, we obtain something like this. Okay, and the whole procedure is we calculate all the Gini impurity scores. If the node itself has the lowest score, then there is no point in separating the patients anymore, and it becomes a leaf node, as in this one. The Gini index of this node was lower than the impurity of chest pain, so we didn't split this node, and we didn't split this node as well. If separating the data results in an improvement, then pick the separation with the lowest impurity value. Okay. So what if we have numerical values without trees? If, for example, we have the weight of a person, what do? Then we first sort all the weights, okay, from lowest to highest. And then we calculate the average weights between all adjacent rows. For example, this is the average of this number and this number. This is the average of this number and this number. Since we have 5 rows here, we have 4 mean values that we calculated. And we will need to calculate the Gini impurity for all these 4 newly calculated values. And the way we do is, for example, we select this one, and the Gini impurity index for this one, we create a subtree with weight smaller than this mean value that goes on the left side, weights higher than this value goes on the right side of the subtree. And since we have only one value here, 155 is smaller than this value, this goes to the left side of the tree. And since that patient who has 155 weight has no heart disease, okay, therefore that patient goes to here with weight smaller than 167 and with no heart disease. And for the rest of the data, 180, 190, 220, 225, they all have weight higher than this number, so they all go onto the right side of the tree. And since we have one patient with no heart disease, we have a 1 here, and we have 3 patients with heart diseases, we have 3 here. Okay, so we calculate all the Gini indexes for these guys, and we keep constructing our trees based on these Gini impurity indices. Okay, so what are the advantages and disadvantages of decision trees? First of all, decision trees are simple to understand and they are easy to interpret. They require little data preparation. They are able to handle both numerical and categorical data. That's an important one. It's possible to validate a model using statistical tests. And the main disadvantage of decision trees is they have a tendency to overfit. If you are not careful, then it's highly likely that they will overfit to your data. Okay. Now let's make a small Python example before we keep going. Okay, that's a very simple example, and we will be using the tree library from scikit-learn, and we will construct a very simple data with 2 points and 2 classes. And let's visualize our data, what it looks like. So it is this simple. There's a 0, 0 here, that's from class 0, and there is 1, 2, that's from class 1. Okay. Now we will use the decision tree classifier from tree in order to create our model and then as usual we will be fitting x and y values to this model. Now we trained our model, we will use the predict as usual to make a prediction, and our prediction says 2 is from class 1, and if we check the graph, the 2 should be somewhere here, and as it is closer to the class 1, it's highly likely that 2 is really from class 1. And what we can actually get from scikit-learn is the prediction probability of 2. And as you see, the prediction probability of 2 being from class 0 is 0, and the prediction probability of 2 for being from class 1 is 1, which means our prediction is 100% sure that 2 is from class 1. And we can do something similar. That's 0.4, 1.2. It says it's from class 1, and it says its prediction probability is pretty high as well. So let's try to visualize our decision tree. Okay, our decision tree looks like something like this. And let's try to visualize the decision boundaries of our decision tree, and we will come back to this tree later. In order to visualize the decision boundaries, we will use this method, and we see something like this. Okay, here we have 1, 2 from class 1 and 0, 0 from class 0. And as you see, there is a strict boundary here. This is the decision boundary of our tree. Since this is a very simple tree, we have a single decision boundary, and this is from y is equal to 1. And if you check the decision tree itself, it says if y is smaller than 1, then that belongs to this class, and if y is higher than 1, then it belongs to this class. And if you check the decision boundaries, that's actually quite true. If y is smaller than 1, then it belongs to class 0, and if y is greater than 1, then it belongs to class 1. And checking our decision probabilities, that's why it is so strict. We had a value from 2, it's basically here, and since the decision boundary here is here, then it's from class 1. Everything that falls within this region, they are from class 1, and everything that falls within this region, they are from class 0. So that was a simple example. Now let's work on a more complicated example to see how a decision tree behaves with certain parameters. So as usual, we will be using our iris dataset, the flower dataset. We will first import our required libraries, and then we will read the data. Then we will assign column names, since the data doesn't contain the column names. For the initial example of iris dataset, we will be using the petal length and petal width. We will not using the rest, the sepal length and sepal width. And since the species are categories with text, if you remember from previous lectures, the species were iris status, iris versicolor, and iris virginica. So these are text, these are not numerical values, so we somehow need to convert these values into numerical values, and this is what we basically do for categorical data. So these first 4 columns are independent variables, okay, and for this example they are numerical values, and our target variable species is a categorical value, so we need to do something about this. And this is how we convert our categorical target variable into numerical variable. Okay. And now our data is ready. We have x and y. Okay. We now declare our decision tree classifier, and then we make a fitting operation. Okay. And now we will visualize our tree. Remember the first tree I have shown you that had 2 levels, the root level and the decision level. Now this tree is much more complicated. As you see, it has quite a few layers. And let's check the decision boundaries and try to understand why it has so many levels. When we look at the decision boundary, that's a more complicated decision boundary than the previous one. Remember, the previous one had a decision boundary that was basically splitting the space from y is equal to 1. And this is a much more complicated decision boundary. And there is something fishy going on here that's trying to overfit, but it's not really overfitting. But with this decision boundary, we come up with a decision tree like this. Okay. Now let's try something different. Let's change the columns we used. We had used the petal length and petal width. Now let's use sepal width and sepal length. Okay. And for this, first let's look at this one with just random state 42. We will not use any other parameters. This is the default decision tree parameters. And when we visualize the decision tree, as you see, this is a very messy, that's a very deep, very strange decision tree. It has so many leaves, it has so many branches, it has so many levels, which means there is something fishy going on with this tree. You shouldn't have this depth with that much data. Okay. So in order to understand what's going on with our decision tree, let's try to visualize the decision boundaries. So once we draw the decision boundaries, as you see, it's trying to really overfit the data. You shouldn't have these little things here. Okay. Your decision boundaries should be somehow smooth. This is really trying to overfit. So what we can do in order to avoid this overfitting problem, let's go back to our decision tree classifier declaration, and we declare another variable called max depth. So this is restricting our tree to maximum depth of tree. Okay. And once we do this, you see we have a less messy decision tree. So we have depth 3, this is level 1, this is level 2, and this is level 3, and this is our root node. This is level 0, level 1, level 2, and level 3. And if you check the decision boundaries, so this is somehow smoother. Okay, it may not be splitting the space in a nicer way. I mean, the performance of the decision tree is worse than the previous one, but the previous one was obviously making an overfitting. So this is a nicer tree. Not saying this is a better decision tree, but this is a nicer tree, and it doesn't overfit, which means it's basically much better for generalization. Okay, so those were two different examples for decision tree creation. We will be doing more exercises concerning the decision trees, but before doing that, let's take a look at how we can use decision trees for regression. So let's define two variables, 0, 0 and 3, 3 with these target variables, and in order to use decision tree as a regressor, instead of saying decision tree classifier, we define a decision tree regressor. Okay, and the rest is the same. We just use fit in order to learn from our data, and then we use predict for making a prediction. And let's see a more complicated example. In this example, we will be creating a sine wave. So this part is creating the sine wave, and then we will basically fit two models, two regression models, one with maximum depth of 2 and the other is from maximum depth of 5. Okay, and then we will be visualizing this data. Let's try to do that. Okay, so these little dots are the data. This is the sine wave with a little bit noise. So with this command we created a sine wave basically, and then here we added some noise, and this is what we came up with. And here we created two decision trees, remember, with maximum depth of 2 and maximum depth of 5. And when you take a look at the graph, the plot, when we have maximum depth of 2, we have these blue lines, which is basic kind of okay-ish regression. But once we have a maximum depth of 5, as you see, the regressor has a tendency to overfit the data. These little things that's going through the data, the noise of the data, this is overfitting. And this is something we should avoid. Now let's see how we can avoid this overfitting when we are using decision trees as regressors. So this is the same code basically. This is exactly the same data preparation code that's creating a sine wave with some random noise. And here this part is same as well. This is maximum depth of 2. But now instead of just using maximum depth of 5, we are using another variable called mean sample leaf. Okay, that's basically saying you should have minimum number of 10 samples in a leaf, otherwise you shall not split this. Okay, even if the Gini index is kind of okay for splitting that leaf, you shall not split that leaf if the minimum number of samples is smaller than 10. So that's basically some sort of regularization for decision tree regression. Okay, and let's see how that works. Again, this is our data, the circles. The blue lines are for maximum depth 2, and the green lines are for maximum depth of 5. Okay, with the regularization, by defining just the minimum number of samples on a leaf, we make a regularization, and right now the regularized decision tree looks more sane. Okay, that's not overfitting anymore. So that's a more generalizable, much nicer decision tree. So that's how we use basically decision trees for regression problems. Okay, now let's see something called end-to-end modeling. Remember what we have done for the regularization? We had a parameter called mean samples leaf. Okay, we usually have some parameters with our models that we need to define, but it's difficult to know by heart what to use for these parameters. Okay, and the end-to-end modeling gives us a tool in order to find out what parameter is best for your case. Okay, so for this example, we will create some circles with make moon, and let's plot what we have created. So this plot is the result of our make moon commands. Okay, we created 1000 samples with some random noise. Okay, and now we will use decision tree classifier in order to split this data into 2. We will create 2 decision tree classifiers, one with the default parameters and one with mean sample leaf 10. Okay, and as we do usually, we will split the training set into test and train, and we will use 10% of the data for testing and 90% of the data for training. And now comes something new. This is grid search CV. So we are trying to find out the best number for this parameter. So we used 10 for the previous example, but we could have used something else. We could use 5, for example. We could have used 20, we could have used 15, but we just used 10. Okay, but we don't know whether that was the best choice or whether that was not a good choice. And the grid search CV does it for us, right? Grid search CV is an exhaustive search over specified parameter values for an estimator. And in this case, our estimator is the decision tree classifier. And in order to use grid search CV, we just define the parameters we want to be searched for. Okay, let's import our grid search CV, and this is how we define our parameters. We just declare the parameter. We say, okay, I'm gonna search for the best value for mean samples leave. This is the name of the parameter we want to search for the best value, and search the value from ranging from 5 to 20. Okay, just try everything exhaustively. That is a time-consuming process, so I'm not gonna go into the details for more than one variable. But if you wanna try it yourself, just uncomment these lines, uncomment out this line, and you will be increasing the number of parameters that grid search CV is basically using. That will take more time, but you will see that it's brute forcefully finding the best value for all these three parameters. In this case, grid search CV will check for and look for the best value for mean sample leave. Okay, let's make our definition, and then we use the command grid search CV. We provide a classifier. We just provided grid search CV the base classifier, base decision tree classifier with no parameters. Okay, and then we provide the grid search CV the parameters it should check for, and then these are some parameters for CPU usage and logging. And then we say grid search CV fits. That's gonna fit a model that takes a little bit time, and then it will give us the best estimator for the parameter. And as you see, the mean sample leave 16. It's not 10, it's 16 is the best for our problem. So let's see how this affects actually our decisions. Let's make an accuracy test. We had split our data into test and training. We trained our model with grid search CV. We have never seen the test set, right? Let's calculate the accuracy with the grid search CV classifier, the classifier the grid search CV trained. Okay, and the accuracy score is 0.83. Now let's just use the base decision tree. What if we haven't provided any parameter as mean sample leave, and what if we haven't provided mean sample leave as 16? Okay, as you see, the accuracy score is lower because that's what basically the grid search CV does. It's finding the best parameter and it's giving you a higher accuracy. Okay, and basically with this get params method, you can check the parameters of your model, and then you can basically provide all these values to the grid search CV. You can just see the parameter name, you can see the default value. For example, for mean sample leave, default value is 1. Okay, that's just 1 because if you have one sample on the leaf, you can split it. But by providing 16 here, we came up with a much better decision tree. So this is how grid search CV works. That's used for estimating or finding the best parameter value brute forcefully. Okay, now let's take a look at another example for chronic kidney disease. That's a new dataset. You can find the dataset in the link. Let's import our libraries and let's read the data, and then let's check what we have in the data. Okay, as you see, we have 25 columns with this data, and the first 24 columns are independent variables, and the last column, the 25th column, is basically our target variable. We have some values concerning the kidney disease, and by using these independent variables, these 24 independent variables, we will make a decision whether the patient has chronic kidney disease or not. So CKD means chronic kidney disease. When we take a look at the first 10 rows of our data, what we see is basically we have numerical values, as in this one. And we have some values with categorical data, like PC, RBC, and PCC. So we have both numerical and categorical values. But we have something else. We have these question marks, right? That means we are basically lacking data here. And that's quite normal when you're doing an experiment. You may have some values that are missing. So we need to have a way of dealing with this, because you can make an experiment, and during your experiment you may miss some values. For example, for this person, you performed the test, you calculated 24 independent variables, but out of these 24 independent variables, 1, 2, and 3 of these variables were missing. So maybe you couldn't calculate them, your tests didn't give results. Therefore, we need to have a way of dealing with this kind of data. So in order to deal with this kind of data, we will need to have an exploratory data analysis. Okay. And the initial step for our data analysis is we will be replacing all these question marks with none, NumP none, because neither NumPy nor mathematics doesn't know anything about question mark. This doesn't say anything about the data. Okay, so we just replace all these question marks with none. Now we have much nicer looking table, right? We don't have any question marks anymore. We have nones instead of the question marks. These are missing values. These nones are called missing values, and we will be using missing values table from helper functions. We will be checking how many columns have missing values. So this is basically giving us a brief overview of our data that says our data has 25 columns. Okay, and out of these 25 columns, 24 columns have missing values, and you can basically get the statistics from this table. For example, for red blood cells, we have 152 missing values. So 152 rows has missing red blood cell values, and you can check for the rest. But this table tells us we have quite a lot of missing values, and we need to take care of that. We cannot just neglect the rows with missing values, because we have limited data and we want to make sure we really make use of the data in a good way. So we cannot just neglect that rows. We need to find a way to fill these rows. Okay, and that's what we will be doing. So in order to sanitize our data, we first need to find out the numerical columns. For this example, we will assign the numerical columns by hand. So these are basically the numerical columns. And we usually first find the numerical columns and then say the rest of the data are categorical columns. Okay. With this expression, we now have the categorical columns as well. And then we need to convert our numerical data. And let's see what we have inside our data frame. We converted everything into a data frame with this expression. Now we have this data frame. You see, we have floating points and we have objects. Okay, and these objects are basically categorical values, and we somehow need to deal with these guys. So let's see the unique values inside our categorical values, because if you remember, we had normal, abnormal, or stuff like that. We had two values usually for the categorical columns. With this command, we basically check the unique values for each categorical column. And as you see, for all but just one, we have two values. And that's how it should look like. But there's something strange going on with this column, the DM column. So let's check what's going on with DM. So when you take a look at the details of DM column by unique, that's basically giving you the unique values, unique categorical values of DM. You see there is yes, there is no, and there is a yes with a blank in front of yes. Okay, and we need to get rid of this, because this is basically a yes as well. We need to have two values. We need to have yes and no. This is not a good thing, so we need to get rid of that. And in order to get rid of that, we use string strip. Okay, and once we get rid of that, when we check the unique values of the M column, we have just yes and no, and that's a good thing. Now we have, for all categorical values, we have two different unique values for the categories. Okay, so now we have categorical values and numerical values with our data set. We need to convert our categorical values into numerical values. We will first deal with our target variable. Remember, our target variable was the class column, okay, and it has stuff like chronic kidney disease and not. So we will convert chronic kidney disease into 1 and the rest to 0. So this is how we will be dealing with the target variable. And once we look at our table now, you see the class is not CKD anymore, but there is ones and zeros. We don't see any zero here, but what we have done with the previous command is we converted the text values, test categorical values for the class to zeros and ones. Okay, and now we will be doing something similar. It's not the same, but something similar to other categorical values. But before doing that, we need to somehow fill these missing values. Once we fill the missing values, we will convert all our categorical values into numerical values as well. So let's drop our class and create x and y values. So x basically contains all the 24 independent variables, and y basically contains our target variable class. Okay. Now we will be imputing, or let's say filling our missing values with scikit-learn impute, and we will be using the simple imputer for that. And what it will be doing as the filling strategies, we will be using the median values of the columns. What that means is we will calculate for the numerical values the median values of that guys, and for categorical values we will be assigning the median value of the number of occurrences of that column. Okay, and for the numerical columns we will be using our imputer fit transform. And once we check, you see we don't have any missing values for the numerical values anymore. We just filled it. For example, if that was a missing value, we assigned the median of this column to that missing values. Okay, and once we check the missing values table, remember we had 24 columns with missing values previously. Now we have just 10 columns that have missing values, and these are basically the ones with categorical values, RBC, PC, and PCC, for example. Okay, now we need to somehow convert these categorical values basically into numerical values, and what we will be doing for that is we will basically use a function called getDummies. Now let's execute that and see what it's actually doing. Once we basically use getDummies, instead of categorical values, we have zeros and ones in the columns. Okay, remember RBC was normal and abnormal. Now we have zeros and one here. Okay, and that's basically a strategy to convert your categorical data into numerical data. We didn't just assign 0, 1, 2, 3, 4 as we did for the target variable, because these are independent variables. And if we assign a value that's much different than another value, that would give a weight and that would confuse our model. Okay, so we need to have a strategy not to confuse our mathematical model, and that's why we use the getDummies in order to do that. Now let's make two simple examples in order to understand getDummies in a better way. We have S, A, and T, and once we use getDummies, for example, instead of S, what we use is, that's not an A, that's an S, that's not a T. Okay, and instead of S, we use, this is an S, this is not an A, this is not a T, and for T, this is not an S, this is not an A, this is a T. Okay, we basically converted S, A, and T into this matrix, this small matrix. Just skip this row. We just converted A, S, and T into the small matrix. Now let's make another example just to make it more clear. So we have IDs and countries. We created a pandas data frame with these IDs and countries, and we come up something like this. Once we use getDummies, what we basically obtain is something like this. Okay, so for country France, this is not country Spain, this is country France, this is not country France, this is not country France. You can follow it from here. So this is country France from here. For country Germany, Spain is not Germany, that's 0. France is not Germany, that's 0. Spain is not Germany, that's 0. Germany is Germany, that's 1. France is not Germany, that's 0. For Spain, Spain is Spain, this is 1. France is not Spain, this is 0. Spain is Spain, this is 1. Germany is not Spain, this is 0. France is not Spain, this is 0 as well. So this getDummies method basically converted our textual data into numerical values. And there is yet another method to do that. That's from scikit-learn. That's called one-hot encoder, and that basically gives something. We first need to obviously import it. That gives something like this. Okay, that's a similar matrix. And for our examples for this lecture, we will be using getDummies. We will be using one-hot encoder for deep learning classes. They are not so different. They basically give quite similar results. Let's work on another example. That's a data set from IBM Human Resources, and that's to understand the attrition of an employee. That's a data set I provided in the links as well. As usual, we import the required libraries, and then we read our data And let's see what we have inside the data. As you see, we have 35 columns. So that's a pretty crowded, pretty big data set. And we have a column called attrition. And apart from that, all the other columns will be used as the independent variables. And as you see, we have categorical data as well as numerical data. We will be using decision trees for the classification problem. And what we would like to understand is based on the independent variables, whether the employee has attrition or not. Okay, we would like to predict this column, attrition column. Before doing that, before fitting the decision tree into our data, we will do an exploration of the data. And with this data analysis, we will try to understand our data. Okay, we have 35 columns, that's what we can observe. We have 34 independent variables. We have a target variable. And let's see with data frame shape. We can see that we have 1,470 rows of data. And let's see what we have else with data frame.info. As you see from the D type column of the data frame.info, we have some integer values as well as object values. And as we had seen from our previous examples, if we see object here in the D type column, that means we have categorical data for that column. So for attrition column, for example, for business travel, we have categorical data. That's what we could be able to observe with data frame.info. Okay, let's try to display the first row of the data. As you see, age is a numerical value. We have categorical data for attrition. For business travel, we have categorical data as well. So as you see, it's more or less from everything. We have a lot of categorical data as well as numerical data. Now let's try to see whether we have missing data or not. As we have seen in the previous example, we need to deal with the non-existing data or null data if we have any. And with this command, data frame is null any, we can see whether there is any missing data or not. And as you see, none of the columns actually contain any missing data. So we don't need to deal with the missing data for this example. Okay, so let's try to use the describe for the data frame. With this describe, we will make some conclusions as well. As you see, we have the mean for the numerical values, and we have the standard deviation for the numerical values as well. And if we look at the data, we can see that, for example, for employee count, we have standard deviation of 0, which means basically this column contains only one single variable, which is 1. Okay, so all rows contain 1 as the employee count, which means basically this column is not usable. Okay, and let's see whether we have stuff like this. Okay, we have a standard deviation of 0 here as well. Standard hours, that's 80 hours for everyone with no exception, because the standard deviation is 0, which means this column should be dropped as well. This column doesn't contain any information, any useful information, so we don't need to use it. It would just make things complicated. It's not gonna help for anything. Okay, and when we look at the column names, actually we can observe something else. So we have employee counts, which is 1 for every row, so we need to drop this. And there is something else, employee number, which is a sequential count. Okay, and when we check the value for employee count, employee number, we can observe that. Let's try to see from the data. So you see, employee number is a sequential number, right? 1, 2, 3, 4, 5. That's going like this. And if we use this as an independent variable, that would confuse the algorithm. That would confuse our model, because it's an increasing number. But that increment doesn't mean things are getting more important. This is just a sequential number, and we need to drop sequential numbers. We cannot use sequential numbers for classification, no regression. So we need to drop this. The previous two columns with standard deviation 0, the employee count and standard hours. If you don't drop this, nothing gonna happen. Nothing bad's gonna happen. But for the sake of simplicity, we can drop this. But if you don't drop employee count, that would confuse the algorithm. That's for sure. We need to drop this. Okay, so let's try to see what we will be doing with this data. So we first need to find out the numerical columns. Okay, and this is basically how we find the numerical columns. And everything else, which is not numerical columns, this is what the statement is doing actually. Everything else is categorical columns. And from this categorical numerical columns, we need to drop employee count, employee number, and standard hours. So this is what we basically do with that. Okay, so the remaining things are call numerical, which is the numerical columns, and call categorical, which is basically consisting of categorical columns. Okay, and there is yet another way of basically finding the categorical columns. As we had seen here, we have integers and objects, and if we check the D type for df info, things with object D type can be classified as categorical columns as well. Okay, so once we create the categorical columns, we can remove them from the all column set, and then we can obtain the numerical columns with that. Okay, that's gonna basically give the same result. And if we print the length, so we have 23 numerical columns. We originally had 26 columns in the numerical set, but we dropped these 3 columns. Okay, and we have 9 categorical columns. Now let's try to analyze more our data. Let's try to see the correlation metrics, for example, for the numerical columns. See, if you remember these core statements from previous classes, it's giving you basically a table. And in the diagonal, everything is 1, and depending on how correlated two variables, it's either a big number or a small number. We can do the same with basically more fancy ways, like heat maps from Seaborn. And the darker it gets, the less correlated the variables are. And as you see here, these variables are pretty much correlated with each other. And some algorithms, some classification algorithms as well as regression algorithms, do not really benefit from things being correlated. So sometimes you need to drop some too much correlated variables, or sometimes you need to take care of this correlation. In any case, it's a good idea to check whether you have correlated data or not. So this is just another way of seeing the correlation between variables, and yet this is giving you another way of seeing how correlated your variables are. Okay, so now we have our categorical columns obtained with 2 different methods. Now let's see what we have in the attrition column. If you remember from our previous example, we had yes, no, and a yes with blank character in front of yes, but this time we have just yes and no. Okay, it's fine. Now we need to convert this textual data into numerical data. Okay, and the way we do this is we just assign 0, 1 and whatever class number to the class. Since attrition is the target variable, we don't need to use get dummies or one hot encoder. These statements we had seen in the previous lecture. Okay, we'll just assign 0 to yes and assign 1 to no. And that's what it does. And now we need to remove attrition from our categorical data because we will be using the attrition column as the target variable, right? It's not an independent variable, so it's supposed to be removed from call categorical. Okay, the categorical column shouldn't have attrition. And once we remove that, you see we have one less. The attrition is gone from our column list. Okay, so comes the important part. We need to use get dummies to convert the rest of categorical data into numerical data. Okay, and that's what it does. And when we check the heads of our categorical data, we see something strange, right? That's educational field underscore human resources, education field underscore human sciences. You see, for every different education field in the category of education field column, we have one column. Okay, and since we had 6 different education fields, it's human resources, life sciences, marketing, medical, other, and technical degree. We have 1, 2, 3, 4, 5, 6 different education fields as the categorical value for education field. We now have 6 different columns. That's what get dummies did. Okay, and the way we read these columns is if the person is from education field life sciences, then this column is 1, the rest is 0. You see, because the guy is from life sciences. Similarly, if the employee is from other fields, then this column is 1, the rest of the columns for that employee is 0. For example, if the employee is from medical field, medical education field, this column is 1 and rest of the columns is 0. And since we had 6 different education fields, we now have, with the help of get dummies, we now have 6 different columns for converting the categorical data into numeric data. That's same for example, business travel. We have non-travel, frequently travel, rarely travel. So instead of having just business travel column as a categorical column, we now have 3 different columns for business travel with the suffix non-travel, frequently travel, and rarely travel. Okay, so we had 3 different business travel types in the categorical column. Now we have 3 different columns in order to convert the business travel categorical value into numerical value. That's same with the departments. We have human resource department, research and development department, and sales department. So instead of having one department's column which contains 3 different classes as sales, research and development, and human resources, we now have 3 different columns that's representing the department's categorical column as a numerical value. Okay, and if an employee is from sales department, then this column is 1 and these 2 columns are 0. And if the employee is from research and development department, then this column is 1, and this column and this column are 0. That's basically the same logic with the business travel or with the education field. Okay. And looking at the gender, for example, instead of having female and male genders, we now have 2 columns, gender female and gender male. And if the employee is a female, then this column is 1, this column is 0. If the employee is a male, then this column is 1 and this column is 0. Okay, now we have our categorical data converted into numerical data, right? But we had other columns. We had original numerical columns. So we need to concatenate these 2 columns, the numerical columns and the newly generated categorical columns, and we need to assign this to X. Okay. And once we do that, as you see, we have all the columns right now. And you see at the beginning of the data frame, we have our original numerical columns, such as monthly rate, number of companies worked. And at the end of the data frame, we have our categorical data that has been converted into numerical data. Okay, now we have a complete data frame on X. And we need to do the same for the target variable. We convert our attrition numerical value into this Y variable. Now, instead of having attrition yes and no, we have zeros and 1 for the target variables. And you see we have 1233 yeses and 237 no's. Okay, and when we check the information, you see we have all numerical columns right now. We don't have any object here in the D column. Okay, that was the whole point. Now our data is ready. We converted all the categorical data into numerical data. We didn't have any missing values, so we didn't have to deal with the missing data. Now we have our independent variables stored in X, and we have our target variable stored in Y. Okay. Now it's time to split our data into training and tests. As we usually do, we import train test split from scikit-learn, and then we will be using 20% of the data for tests and rest for training. And we will be using a decision tree classifier. We will be using a bare classifier. We will not give any parameters. You can try giving some parameters. You can change the parameters to see the effect. And we declared our model here. We use our training X and Y variable for learning. Now our model is ready. Okay. Now let's see how well our model worked. We will be using accuracy as well as precision and recall. In order to do that, we import these libraries from scikit-learn. And then let's see, for the training set, the test we used for learning, we have an accuracy of 1. Okay, that's perfect. Again, for the training sets, we have a precision and recall of 1 as well. So the decision tree is perfectly splitting our training data, and that's just working perfect for the training. But let's see how it's gonna behave for the test. But before that, let's see the confusion metrics. You see there are no false positive, no false negatives. These are 0. That's a perfect split. Okay, let's see what we have with the accuracy score of the test. You see that was 1, but right now it's 0.768. That's not bad. That's not good either. The accuracy by itself is not a very good measure, so we need to check the precision and recall values for our test. And when you check the precision and recall values, they're not really high. They're below 0.5. That means our model is not really working very well for the test set. It just memorized the training set. That's why it gave an accuracy of 1 and precision and recall 1. But for the test set, it's not really behaving that well. If you check the F scores, that's not good either. So our model is not really good. That's something we can conclude, and we can conclude this from the confusion metrics as well. You see there's a lot of false positives and false negatives. That means our model is not really behaving in a good way. But what we have done basically with this example is we converted our categorical data into numerical data, and then we could be able to use decision trees for classification. You can try yourself with different parameters here. Since we use just a bare decision tree, you can define a minimum number of samples per leaf, or you can basically define the maximum depth so it doesn't overfit. In this case, for example, the tree perfectly overfit the data. That's why it has an accuracy of 1. And you can give it a try and try different things. So to summarize this week's lecture, we have seen decision trees. We worked on the definition of decision trees. We have seen 2 different ways of visualization. One visualizes a tree, one visualizes decision boundaries. We have seen how we can construct decision trees. We have seen Gini impurity index, and we said we choose the node with low impurity for the root, and we keep doing that. We always select the nodes with lowest Gini impurity for reconstructing a decision tree. And now we have seen we can basically use decision trees for regression problems as well. We have seen a very important command from Python, that's grid search CV, which exhaustively searches over specified parameters for an estimator. And then we have seen a way of converting categorical data into numerical data. So that's basically it for our 6th week. I hope you enjoyed that. See you next week.